Welcome back, everyone. I'm Professor Rhett Smith from ProtonGuru.com. Today we're going to go over Lesson 4.7 in the Organic Chemistry 2 Primer 2021, and we're going to start learning about the reactivity of aromatic species. We're going to talk about reactions that benzene can do specifically. Now, benzene has all these double bonds in its structure, if you remember. So we want to talk about what we know about how double bonds can do reactions. And we talked about, in Section 3, a lot of reactions where electrophilic addition to these pi bonds is involved. So let's consider just the electrophilic addition of an acid. So if we look at what the product will be, we know that we make a carbocation intermediate. And we try to make the most stable carbocation we possibly can. We'll see in the next few lessons that making the most stable carbocation is also a trend for any time you make a carbocation from an alkene that happens to be in a benzene ring. Now, what do we know about carbocations? Well, one thing the carbocation can do is have a nucleophile add to it, right? And this is what we see in a lot of the reactions of isolated alkenes. Another thing we know is that if you make a carbocation, say the carbocation you make in the course of an E1 reaction, well, then the next thing you can do with that carbocation is electrophilic elimination. If we do that, we will make a double bond. So we're going to use these two types of steps, the electrophilic addition and electrophilic elimination steps, as parts of reactions that benzene compounds can engage in as well. Now, benzene is much more stable than an isolated alkene, so it's much more difficult to break the pi bond by electrophilic addition in benzene than if we had an isolated alkene. But it is possible. So let's just say for now, not knowing what electrophiles we necessarily need, let's just say we generate this carbocation. Well, there are two things I talked about in the previous page that a carbocation can do that we know of. You can either have a nucleophile come in and coordinate to that positive charge, and in this case that would give you this species, or you can do the electrophilic elimination that I mentioned in the previous page, like we would see as part of an E1 reaction, and make that double bond back again. Now, if we were to do this pathway shown at the top, you see I've already kind of scribbled it out in the hopes you wouldn't try to memorize it or write it down as a good pathway. It says no, this would destroy the aromaticity. All right, so if we start with benzene, we end up with this compound that if you can't see it under my typing over it, will look like this, Y and Z. That compound's not aromatic. We've broken up the pi conjugation around the ring. That would be very unfavorable to go from a very stable aromatic species to a much less stable non-aromatic species. So that's not the favored pathway. If instead we take a proton away and remake the double bond, well, we're aromatic again with the 6 electrons pushed around the ring. And the net result is that one of the hydrogens on a carbon is replaced with your electrophile. So we've taken one group off and substituted it for another. This is a substitution reaction. This is a type of reaction that happens on aromatic species specifically, and we need an electrophile to get that reaction started. So this reaction is called the Electrophilic Aromatic Substitution reaction, very commonly abbreviated EAS. Electrophilic aromatic substitution is a two-step process. First, electrophilic addition of some electrophile, and that's going to be the slow, difficult step because in that step you make a less stable intermediate temporarily before you have step 2, the electrophilic elimination, in which you reestablish the aromaticity, regain the stability you temporarily lost. And of course that step is very fast and easy to do. So let's draw this mechanism out without all the extra potential pathways that don't happen. So step 1, you have an electrophile that will add. You should be able to draw out the intermediate species you would get. So here's your electrophile that's added. We haven't taken this proton off yet that was on this carbon. We have a proton in each of those 2 carbons, of course. We'll draw those in because those 2 carbons are involved in the mechanism. That leaves this carbon with only 3 bonds, so it's a carbocation. So now, in order to reestablish the aromaticity, we take the 2 electrons from the hydrogen, dump them in there. That H+ group would leave the molecule now with reestablishment of this double bond and the aromatic core. So what are we going to do in the rest of this lesson? Well, we're going to learn several different types of electrophilic aromatic substitution processes. They all follow the same exact mechanism. They're just going to use different electrophiles. So the only really unique thing we need to look at in the rest of these lessons about electrophilic aromatic substitution is what the electrophiles are and what species we need to react together to get those electrophiles. The first two electrophilic aromatic substitution reactions specifically we're going to talk about were two that were discovered by Friedel-Crafts. And what they did is they used compounds like aluminum trichloride and an alkyl halide, which would react with one another to make some sort of electrophile in the presence of benzene. Now what they observed when they reacted this alkyl chloride with aluminum trichloride in the presence of benzene is that you would substitute one of the H's on benzene for an R group. So the piece that ends up attached is this R group. If you look back at the general mechanism we learned, that means we need an R+, right? And a carbocation must be the electrophile in this case. So what we really need to figure out is how do I get the R+ from the interaction of these two species so they can make the R+ before it reacts with benzene? Well, let's think about this aluminum trichloride reagent a little more carefully before we figure out the mechanism down here. Aluminum is in the third tall column of the periodic table near boron. And that means it has an empty p orbital on it, and it does not have an octet of electrons yet at aluminum. So that aluminum is going to be very, very attractive for a lone pair of electrons to fill the unsatisfied octet. And there are 3 lone pairs on an alkyl chloride that could serve this role of being attracted to the aluminum center. So if I take one of those 3 lone pairs from chlorine and donate it to the aluminum, well, I really don't want to leave 2 bonds to the chlorine. Remember that a neutral chlorine should have only 1 bond. So I'm going to have to pull the electrons away from the R group. And what do I get in this case? Well, the R group has then become R+, which is good. We decided that's what we needed so we could attach it to the benzene. And the aluminum sitting over here now has 4 chlorines on it. So we have what's called a tetrachloroaluminate, which is a minus charge on the aluminum. So you make this salt. And it's the R+ in the mechanism for the electrophilic aromatic substitution that serves the role of the electrophile. So you have the pi electrons attracted to the R. Temporarily, you lose the aromaticity, and the R group is attached to the same carbon as one of the hydrogens. And you leave a plus charge here. Then you reestablish the aromaticity by losing the H as H+, and in that way you would get the net effect of substituting one of the H's for an R group, which is what Friedel-Crafts observed when they did the reaction. We should be reminded that anytime we make a carbocation intermediate, an R+, like we just did, like we saw for the SN1 reaction, or the E1 reaction in section 2 of our book, any reaction where a carbocation intermediate is formed requires us to think about whether that carbocation might rearrange. Carbocation rearrangement happens very, very, very quickly before any subsequent steps take place. So in the case of our Friedel-Crafts alkylation reaction, the rearrangement of this carbocation would have to take place before we had the reaction of the R+ with the benzene. So we need to think about that. So just to remind you, a carbocation rearrangement occurs spontaneously in a very thermodynamically favorable exergonic fashion anytime that rearrangement leads to a more stable carbocation. So if I was to make a primary carbocation in the course of a Friedel-Crafts alkylation reaction, let's say, which is very doable, but beside that primary carbon with the plus charge you see a tertiary carbon, well, you can move that hydrogen over, and that would give you a compound that looks like this. We had 2 H's on the right-hand carbon, like this. We have now the third H, the H that had moved over, leaving the carbon on the left with a positive charge, going from a primary carbocation to a tertiary carbocation, very, very favorable. That would happen before the next step in the Friedel-Crafts reaction. Likewise, I could even have a secondary carbocation like this, and maybe I have a quaternary carbon beside it. Remember that an alkyl group can move if there's no proton present, so this whole R group could move over. The resulting carbocation would look like this, filling in the 2 groups that were already on that left carbon, but moving the R group over to it as well, leaving the carbon on the left with a positive charge. But again, we've gone from a secondary to a tertiary, which is a very favorable process, so that will happen spontaneously as well before that carbocation does any other steps in whatever reaction it's involved in. So let's think about that when we are doing this reaction. If I take this alkyl chloride in the presence of benzene, and I have aluminum trichloride, say, well, what does aluminum trichloride do? The aluminum really needs a lone pair. it tends to tear chlorine off of atoms by having one of the lone pairs come in and be attracted to the aluminum. And we can show that down here. Say, okay, the chlorine is going to be attracted to the aluminum, ripping it off of the carbon to which it used to be attached. So the aluminum with its 4 chlorines as an anion will be present. But then we have this T-butyl group on the carbon. Well, we just tore the chlorine off that carbon, so it lost one of its 4 bonds, and now it's a carbocation. Well, before that carbocation does anything, like reacting with the benzene, we have to check to see if it could rearrange, especially given that it's a very unstable primary carbocation right now. And we look beside it, and we see that there's a methyl group that can shift over to the 1,2-methyl shift type of carbocation rearrangement. That leaves only 2 of the methyl groups remaining on the left-hand side. We took one of them away. And here's the carbon that used to be the positive charge. Now it has this CH3 group that moved over. So let's highlight that by drawing out its CH3 formula. All right, there were already 2 H's on this carbon when it was a carbocation. So now you have a nice carbon that's neutral with 4 bonds. But this carbon on the other side has lost one of its 4 bonds, so it's a carbocation. But now it's tertiary. That will certainly be very, very spontaneous. Remembering that we don't need to draw in the H's or the symbol for the CH3, that carbocation could be drawn out just like that. So let's draw it like that as we do our electrophilic aromatic substitution reaction. So we have this tertiary carbocation, so the benzene will donate its electrons to that carbocationic site. That leaves you with a bond from the carbon on the benzene ring to that site. Right, you have a methyl, methyl, ethyl, methyl, methyl, ethyl. So keep track. A lot of students will sometimes lose or gain carbons when they do this accidentally, so be careful. We didn't do anything with those 2 pi bonds, right? They weren't involved in the arrow pushing. But this double bond has been removed, and those 2 electrons are now being used to make this bond. Well, there's already a hydrogen here, right? We didn't take any hydrogens off of the benzene. There's a hydrogen here, but what we've done is we've left this carbon with only 3 bonds, so it's a carbocation. But we want to reestablish the aromaticity in the faster of the steps, and we're able to reacquire the benzene structure. Here's the carbon we attached with its methyl, methyl, and ethyl group, and now we have the correct final product for this Friedel-Crafts reaction. If you just attach the group without doing the rearrangement, you would find a product that's not formed in very good yield at all. So the correct net product could be drawn out like this. So that reaction of an alkyl halide with aluminum trichloride is a new way to make a carbocation that we've never seen before. But I want to point out that there are other ways that we already know that we can generate carbocations, and we can use those carbocations in this Friedel-Crafts alkylation reaction just like we used the carbocation I showed generated from the aluminum trichloride with an alkyl chloride. So for example, when you take an alcohol in the presence of an acid, right, say we're trying to do an E1 reaction with this alcohol. Well, the sulfuric acid will protonate that O, and then you'll have loss of the leaving group, and you'll get this carbocation. Well, if I did this, but I didn't just have the alcohol and sulfuric acid, and I also had benzene around, now you have an example of an alkyl cation with benzene, and you can do an electrophilic aromatic substitution reaction with those. I'll show you an example of that in a second. This way to form a carbocation from an alcohol with an acid is described in lesson 2.11 if you want to review that. Now in section 3 of the book, we have several reactions where an alkene can react with a strong acid to make carbocations as well. So if I have the alkene with H+, I can donate the electrons to the H+, and here I'd actually get a mixture of 2 potential carbocations where the plus charge could be here or here, and I say that both of them are possible and likely because they're both secondary and have similar stabilities. But these are examples of R+ alkyl that can then react with benzene to do a Friedel-Crafts reaction. So let's take a look at how these conditions and ways to generate carbocations could be manifest in Friedel-Crafts alkylation context. Here we have benzene with sulfuric acid and alcohol. So when you see that, you need to think, okay, these reagents will react with one another in some way, and then something will react with benzene after that. So we just talked about the fact that the sulfuric acid can protonate an OH group and have it leave as a leaving group. So we'd have a CH3, CH2 cation. there's no chance for that to rearrange to anything but a primary carbocation, so that will react directly with the benzene in the electrophilic aromatic substitution reaction. And we know that the net result of the electrophilic aromatic substitution reaction is substitution with attachment to the positive carbon. CH2 was the carbon that had the plus charge, and then there happens to be a methyl group substituent beside that. So the net result is that we make this ethyl benzene as our product. Well, how about reaction of ethylene with sulfuric acid with benzene? Well, the ethylene and the sulfuric acid will react with the electrophilic addition of the proton from sulfuric acid to the ethylene. So we have CH2, CH2. We've done electrophilic addition of the H to one side. In this case, we have the same substituents on each side of the ethylene, so we don't need to make a decision about which would be more stable. And then when this reacts with the benzene by the electrophilic aromatic substitution pathway, we see again that we'll make this ethyl group go onto the benzene to substitute for an H. And again, we make ethyl benzene. So same product in each of the first two reactions. Well, this new way we just learned for generating carbocations involves aluminum trichloride and an alkyl halide, where the aluminum trichloride is very good at yanking the Cl off because the aluminum doesn't have an octet of electrons. It's a very powerful Lewis acid. That again will leave you with this ethyl cation, CH3, CH2 plus. And just like up here, we have the same ethyl cation generated in different ways. The net result is that we're going to get ethyl benzene as our product. This kind of illustrates for you the three different ways to generate carbocations, the way these reactions might be presented to you, but it shows you that regardless of how you make the carbocation, the same principles apply in using those carbocations for the electrophilic aromatic substitution pathway. So Friedel-Crafts discovered that aluminum trichloride could pull chlorines off of things that weren't just alkyl chains, but they could even pull chlorines off of acyl groups. Now an acyl group is the name that people give for this sort of ketone group when it's named as a substituent attached to some parent chain. So an acyl something or other. And what they observed is that the net reaction when you had aluminum trichloride in one of these acyl chlorides is that the chlorine would come off the acyl chloride piece, right? You can kind of hypothesize that's probably pulled off by the aluminum. And you get this ketone with a benzene on one side, and whatever R group is brought in by the acyl substituent will be there as well. So like any electrophilic aromatic substitution process, we need to think, well, how is that electrophile generated? We know that the electrophile we need is going to be R C-1O with a plus on the carbon because it's the carbon that's attached to the benzene. It has to be the positively charged element. Now, this cation has a particular name as well. When you take an acyl group and you make it a carbocation, you name it acylium. Right? Anything with an IUM ending, like ammonium or phosphonium or acylium, tells you it's cationic. And this is generated in exactly the same way that you generate the alkyl cation that we talked about for the Friedel-Crafts alkylation. The aluminum has this empty p orbital because it's in the third tall column of the periodic table, same family as boron, and that will get you this carbocation, carbon R plus. And for charge balance, the tetrachloroaluminate is also floating around. The one thing about this acylium cation, if you read about it in different books, you'll see that, of course, you can draw resonance contributors where I push the electrons towards the carbon and make a compound that looks like this. Regardless of which of these two structures you see as the resonance contributor, it's the same species represented in one of its resonance contributing structures. One other thing I want to mention is that the acylium carbocation will not rearrange. You'll never move this plus charge to some other carbon next to it because, as I mentioned, if and only if the plus charge is on the carbon right by the O, then you can have this resonance stabilization. You're not going to move the plus charge away from being resonance stabilized, so you don't have to worry about that step like you did in the Friedel-Crafts alkylation. Alright, so we've seen two different reactions here. They both follow really the same sort of pathway. First, you generate a carbocation, whether that is acylium or an alkyl cation. And like every electrophilic aromatic mechanism, you do the electrophilic addition, followed by the electrophilic elimination. And in the next few lessons, we're just going to keep repeating this process for different variations of the electrophilic aromatic substitution process. We'll see ways to put different groups on here. So we'll use different reagents, but the mechanism will always be electrophilic addition, the plus charged species, followed by electrophilic elimination to reestablish the aromaticity.